This is tutorial 12, again, part 3. So what is this part going to be about? As you remember from the first two parts, we've been discussing how to determine the types of singularity of a complex function and how to calculate residues of them. And it turns out that this topic is quite huge because there are various approaches to this problem. The first one, which was covered in the very first part, was the best one because and it consisted of expanding your function into Laurent series. And it turns out it was the best method because you sort of killed two birds with one stone. If you had an expansion of your function tolerance series, you can immediately see the type of the singularity and residue at the same time. But unfortunately, it's not always possible to expand your function in tolerance series. And that is why my tutorial 12 part 2 was devoted to this sort of short count, uh, how to do this, how to perform your task of determining type of singularity and residue of the function without expanding a function to Laurent series. It was a very nice method actually, but unfortunately it had its limitations as well, of course. And I gave you two examples at the end of previous tutorial to confirm this idea. So what do we know? What do we need to do now? So, as you remember from the very beginning of our tutorial on tutorial 12, so this is the very first page of tutorial 12. So we discussed methods which allow you to determine the type of singularities and shortcuts. So we already discussed the first method, which was about expansion into Laurent series. It was in tutorial 12, part 1. Method 2 was discussed in part 2 of the same tutorial, and now finally the time comes for method 3. So let's write it down. Method 3. Method 3. So method 3. Method 3. So, what is this method about? Let me take your note again. Note, another note. So again, just like for method 3, unfortunately, it is only for poles. So this method, it is for poles only again. For poles only again. Just like previous method 2. But it's more general. But more general. Let's write it down. It's more general. But more general. It doesn't require what is more general about this method? It doesn't require our function f of z to look like this beautiful form phi of z, some phi of z divided by z minus z0 to the power of m. There was another requirement in this beautiful theorem, namely that the nominator shouldn't be equal to 0 at the point z0, but we are not going to talk about it. So the main thing about this method 3 is that it doesn't require our function to be of a specific form, but the cons is you need to perform 3 steps, quite new steps to be honest. You need to perform 3 steps. That is a drawback, of course, but luckily we still have this method. Okay, step one, determine the type of singularity. Determine the type of singularity. Let's denote it as z0 as usual. Okay, how can it be done without expanding into Laurent series? That's a question we are going to discuss right now. But let me outline these 3 steps for you first. So step 2, if it is a pole, find m, find the order of the pole using method 3. Again, This sounds like something new, and it is something new. So as you can see, all these words are pretty familiar for you, but the thing is that we are going to do both steps 1 and step 2, using absolutely new methods. And only step 3 will be familiar for you. So find residue using the same formula, as we used before, using the same formula. Remember this formula with the factorial, limit, and so on. Maybe it's better to write it down here immediately. So as I said before, this method 3, as well as method 2, by the way, is only suitable to poles. So it works only for poles. But on the other hand, poles are very, frequent in complex number theory, at least in your tutorial sheets, in your tests, and so on. So it's not for nothing that so much time and effort has been devoted to describing poles. Okay, I'm not finished with my algorithm yet. So I wanted to remind you this formula as to how to find residue in the Z0 if Z0 is a pole of order m. So let me remind you, 1 divided by m minus 1 factorial. Then you need to put limit here, limit when z tends to Z0. Z0 is point of singularity. Then you need to take a derivative of order m minus 1 of the function, which looks like f of z times z minus z0 to the power of m. And if you remember from the previous video, when we were discussing method 2, the whole expression inside this brackets was actually equal to phi of z. This was very convenient, very handy, and maybe you couldn't even understand why I'm going into this length of writing this function phi of z in such a long way, But the thing is that now it's going to be crucial. Now we are not going to have any phi of z. We are not going to have this structure at all, and that is why this is going to be crucial. So this was introduction. Now you know what awaits you in this tutorial. So let's move to something more concrete. So let's start discussing step 1. So step 1 is about determining the type of your singularity. So let's write it down. How to determine. Let's blur again. No, not maybe so much. How to determine the type. How to determine the type of singularity. Z0. Until now, we've been familiar only with one method. We needed to expand our function into Laurent series, and then we looked at our principal part. There was another method, but it was specific only for poles. If you were using method 2, then you just needed to look at the function. So you immediately determined that the type of singularity was pole of order m and so on. But now we don't have anything like this. And it turns out there is a second method. Let's outline it. So let Z0 be singularity point for our function f of z. So how to determine its type? It turns out that it sounds even easier. Find limit of your function at this point when z tends to z0, and let's denote our result like 8. So it sounds even easier than expanding into Laurent series. But you know what? There are some not very simple things here at all. So you may end up having 3 different results. And as usual, I prefer to organize everything in columns. So the first column, the second column should be here, and the third column. So what is in the first column? So if your result, if your limit is constant, some constant, it can be 0, non-zero, it doesn't matter, constant, then Z0 is a removable singularity, removable. So that's how easy is determined to the type of singularity by calculating the limit. But you know what? Even more beautiful result should be written here in the first column. It turns out that when your singularity is removable of a removable type, in this case, a residue is always 0 at this point. So this is really beautiful result, very inspiring. And you know the reason, because if you compare this reasoning with expansion and tolerance series, you should remember that removable singularity meant that there's no principal part at all. There's no principal part at all. Zero. Do you remember this number of terms in principal part? It's just zero, including the term with the power of -1. Do you remember that residue was coefficient in front of this of our 1 minute? So there's no wonder that this we get this beautiful result. But it's very convenient to organize it in separate column. Okay, so what is the next case? The next case is if your a, your limit, turned out to be infinity, then z0 is pole. That zero is pole. Very beautiful. But you know one, when we have pole, we always face the challenge of determining its order. And I'm going to talk about it later. So this second column is going to be the hugest column, the biggest column, actually. I'm going to continue it on the next page, but only after I finish the whole table. So, and the third case should definitely be devoted to essential singularities, remember. So how to determine it? It turns out that if your limit doesn't exist, doesn't exist, doesn't exist, very interesting phrase, then it turns out that that zero is essential. And now probably you have a feeling that something really terrible is awaiting you, because what does it mean that a limit doesn't exist? Maybe some of you were under the wrong impression that maybe it's the same, that limit is equal to infinity. No, you know, there is a difference between limit being equal to infinity and limit not existing at all. And that is why let's discuss the third column. How on earth can you determine that your limit doesn't exist? That is why there's going to be continuation of the third column. So hint, we need some hint, some idea or something like this. It turns out that guys like e to the power of infinity, sinus of infinity, cosinus of infinity, and as well as hyperbolic sinus of infinity, and what else? And hyperbolic cosinus of infinity, they don't exist. It turns out they don't exist, at least here in complex variable theory. Do not exist. Do not exist. So what you should just memorize it. You just get used to this step. You should take it for granted, sort of. It does require some proof, of course, and it can be proved very easily, but we don't have time for it, and it's not our intention. It's a goal of your lectures, to give you this theoretical groundwork. My task is just to show you some tricks as to how to solve problems. So what does it mean that this you should just take it for granted that e to the power of infinity or sinus infinity just don't exist. But how to use it in examples? Let's write some one example. One example is enough, I think. One example here in the same third column. So let's imagine that our function is e to the power of 1 divided by z. Well, of course, you recognize this function. I think that we already dealt with this function in our previous tutorials. So, of course, you immediately realize that z0 is equal to 0 is a singularity point. Singularity point. But for some reason, you don't fancy expanding this function into Lorentz series. Maybe you don't remember. Maybe you just don't like expansion. You decided to try out this third method. What should we do in this case? We need to find the limit of our function according to our rule when z tends to z0. In our concrete case, it will be rewritten as z tends to 0, of course, to our singularity point, and function is this one, 1 divided by 0. So, and what do we do here? What do we have here? We should do it sort of in steps, the calculation of this limit. So the first step is just to look only at this fraction. Only don't look at e to the power of something, just at this fraction. And you need to decide where what is the limit of this fraction. So z tends to be 0. It means that the denominator of this fraction is becoming smaller, and smaller, tends to 0. As a result, the whole fraction will be tending to infinity, of course. And now you have exactly the same situation which I pointed to you out before. E to the power of infinity. And this, in this case, your result should be written in words. Doesn't exist. Doesn't exist. doesn't exist. So that's how it happens. And that is why, by the way, our conclusion will be that z0 is equal to 0 is essential singularity. So that's how it happens. So please remember that you should just take for granted this fact that e to the power of infinity doesn't exist, and sinus, cosinus, and all these functions, they just are combinations of the same function. That is why they also have the infinity. Probably this topic was covered in your lectures. I'm not sure. So if you're really curious, you can have a look either at your lecture recordings, or maybe study guide. I'm sure that they should be covered. Okay, but now it's time for us. But in any case, on the other hand, you notice that this task could have been much more easily approached by expanding it to Laurent series. Maybe it sounds even easier. But it's always a nice idea to look at the same problem from different angles. Okay, but as for poles, we definitely need to expand the second column. Because it's going to be much bigger. So I'm going to do like this. So this is expansion of my second column. Because as always with poles, we need to determine its order. So let's call it step 2. According to our algorithm, which I outlined you in the previous page, let's have a look at our very first page. So we are finished with the first step. We now know how to determine the type of singularity point without expanding to Laurent series. So let's move to the second step. How can this be achieved? Namely, how can we determine the order of the pole without, some new method? What is method 3 saying to us? Okay, so let's write it down. If Z0 is pole, how to find its order? How to find its order? We always denoted this order like letter M. And let's discuss it here in this extension of the second column. Okay, so I'm trying to organize this space properly. Okay, maybe even this is enough. So this is second column, Okay, it turns out that you need to do a little bit fancy, maybe annoying thing. So you need to consider the limit. Consider the following limit. Consider the limit. So limit when z tends to z0 to this pole of expression which looks like f of z times z minus z0 to the power of m, and you need to calculate this limit. But you know what? The problem is that you don't know what m is equal to. This is the thing, on the contrary, which you want to determine. So this is like unknown in this equation. And what is equation? Your result shouldn't be equal either 0 or infinity. So what do you need? What exactly do you need to do with this equality, with this limit? You need to play around with m. You need to find such value of m where this requirement is met. So you need to find the value then when you get some decent, some good constant here, not 0 and not infinity. And limit, of course, should exist, not like this. It sounds really fancy. Let's write it down. Where m is unknown. Where m is unknown. You want to determine for this. So this looks like quite a fancy method, Of course, it does look like a formula, like an expression which already came across in the formula for residue. Do you remember this step here? I wrote down this very familiar formula. It does look like this expression, but it has nothing to do with it this time, unfortunately, because m was known for this formula, and now you have no idea what is m. So, and then after you determine m, it will be the order of your pole. So after you determined m, you know that m is the order of pole z0, the order of pole z0. And after that, you should be able to perform step 3. Step 3 was just very familiar for you. Step 3 consists of applying this formula to calculate residue. That's it. So now it's time to practice. So now you know what exactly you should do. So step 3, okay, let's write it down. Nevertheless, to finish our second column, step 3, apply formula. Apply our formula for residue at pole Z0 of order M. I'm not going to write down this formula. So we're already reading it, and we are going to read it once again in our example. So this is the algorithm. This is the theoretical basement for you. And now it's time for us to do examples. Examples at last. Examples. Example. The very first example will be question 1a. Once again, by the way, question 1a. We already dealt with question 1a. So it was hyperbolic sinus of z divided by z. And the assignment so far has been the same for us all the time for the whole 3 tutorials. So determine the points of singularity and find the residue at these points. So how can we approach this task? At first glance, by the way, this function does look like the function which which is suitable for application method 2. But you know that the looks can be deceptive, as we know, because apart from the similar layout for the function, you also need to check the second requirement, which is about nominator. In our case, sinus of 0 should be non-zero, but in our case, it's 0. We already discussed it before. So let's try and use our new method. Step 1. What is step 1? You need to determine the type of singularity. Okay, but I haven't written down the singularity. Singularity, of course, is 0. Okay, it goes without discussion, but nevertheless. So you need to find the limit of your function and this point. So in our case, this limit would look like z tends to 0 sinus hyperbolic of z divided by z. If you try to just plug in z everywhere, you will end up having this uncertainty. This is a classical situation where you can't give the answer to the limit, and you should apply some trick. What trick should be applied in our case? You know, there are some very famous limits. Let's call them famous limits, which you're supposed to know because they are so famous. So the first famous limit is limit of sinus z divided by z when z tends to 0 is equal to 1. Of course, you immediately recalled this limit because it's super famous. You know what? As well as, but you can see trigonometrical sinus. The same remains true for hyperbolic sinus. It turns out very nice fact actually. So now, in our limit, we have nothing else as this famous limit, which of course is equal to 1. And what is important for us, according to our table? Where's our table? So we go here to the first column because A is constant. So this is constant. This is case number 1. And it means that our singularity is removable. Okay, so Z equal to 0 is removable singularity. As you can see, it wasn't terribly difficult. But moreover, even the better news is that if you're dealing with removable singularity, the residue is just equal to 0. In residue, you don't need to go into trouble of calculating all these things. No, is equal to 0. That's it. So this is our answer. Singularity is removable and residue is equal to 0. So sometimes things are pretty nice, you know. But in other cases, you need to show a little bit of, reasoning, a little bit of experience, and so on. So the second example will be just of my own invention. It's not taken from tutorial sheet, it's just my own invention. So f of z is equal sinus z divided by z squared. So, and the assignment, of course, is the same. You need to find points of singularity, determine their type, and calculate the residues. And my intention is to use only method 3. I'm going to pretend that I don't know anything about Lorentz expansion. I'm only armed with this method 3. So the point of singularity is pretty obvious, it's 0. But let's start with step 1. We need to determine the type of this singularity. To this end, we need to calculate this limit again. So limit when z tends to 0 of our function sinus z divided by z squared. Again, it's recommended to start calculating a limit by just plugging it 0 in our case. You will end up having the same situation, 0 by 0. But you know what? This time you can't see any famous limit here because it's not z, it's z squared now. But you can do some transformations. You can sort of separated this beautiful limit, this famous limit, from the rest. Look at this. How can it be done? Sinus z divided by z at times 1 divided by z. It's still true, this, because this expression could be easily written like this. But you know what? This expression is our famous limit, which goes to 0. And that is why we are left with the remaining expression. Let's try and calculate it, because you can substitute this the whole yellow expression by 1. And finally, this is what is left of our function. Let's try and plug in z equal to 0 again to this expression. What are we going to have? 1 divided by 0 obviously tends to infinity. So it means that this time we are inside the second column. If your result is equal to 0, this is pole. Okay. So we have our first conclusion. Our point 0 is actually pole. But more pole means quite like long story, unlike the previous example. Pole means that now we need to determine its type, not type, sorry, order of the pole, order M. How can it be done? And we've never done it before. I only described this method for you. So what do we need to do? We need to consider this special limit. Limit, let me remind you, limit when z tends to z0 of this expression, f of z times z minus z0 to the power of m, and the result shouldn't be equal 0 and should be equal to minus infinity. And we should find m in here. We should start playing around with m until we realize, oh, this is the m, exactly the value of m which I need. So let's rewrite this expression for our data. So z in our case is equal, tends to 0. Our f of z is here. F of z is sinus z divided by z squared. And here we need to write this expression. Z minus 0 will be just z to the power of m. And now we should be cautious about, we need to determine this m. But you know what? First of all, I need to simplify this expression again, because this sinus is really annoying. If you just plug in z0 here immediately, you will end up with some messy situation. 0 divided by 0 times 0, you will never be able to give the answer. I think we should repeat this trick which we applied in the previous step. We need to separate this expression, sinus z divided by z, then substitute it with 1, and after that our function will be simplified and we should be able to see something really sensible here. Okay, let's do it once again. So sinus z divided by z goes separately, and z to the power of m divided by z goes separately as well. So now we can realize again, oh, this is our famous limit. It tends to 1. And after that, our expression gets simplified really considerably. Z to the power of m divided by z. And so, and we need to get a result which is not 0 and not infinity. What is the number of m which satisfies this conclusion? You know what? The only value of m is equal to 1. You know why? Because z divided by z will get cancelled out and it will be equal to 1. And limit of 1 will be 1, of course. So limit of 1 will be 1, and it does require this limitation. 1 is equal to 0, obviously, and 1 is not equal to infinity. And it turns out this is the only value which can give you such a beautiful result. In any other cases, if you substitute m to equal to 2, for example, z squared by z will be z, and limit of z will be 0. No, this requirement is violated. And also, if you try to plug in m like equal to -1, but it could be -1, of course, because order of the pole is always positive. So that's it. So our pole is order 1. I think it's called simple pole or something like this. It doesn't matter so much. The most important thing that we know now, we know that our pole has order 1. So is this our conclusion? Z0 is equal to 1 is the pole of order 1. And now we are ready to move to the third step, to the last step, which is pretty familiar for us. We already had some experience with this formula in the past, but of course I'm going to write it for you once again. So residue of your function, if z0 is a pole, should be can be calculated by using this formula: dm minus 1 dzm minus 1 of the expression f of z times z minus, oh, I need space even, z0 to the power of m. So that's why we did tm, because m is everywhere in this formula. Okay, in our case, it will be m is equal to 1, right? That is why 1 minus 1 will be 0 factorial, and you know 0 factorial does make sense. It's just equal to 1. I'm not going to write it. What about derivative? Derivative will be of order 0. What is derivative of order 0? Sounds really strange. It means no derivative at all. You just need to write this expression, and that's it. Very nice. So all that is left for us to do, we need to plug in our function here, which is sinus z. No, limit. I forgot the limit, sorry. My formula is not quite right. How to insert the limit here? It should be limit after factorial when z tends to z0. Sorry for this. I made a mess out of it. Okay, but at least I found a mistake almost in time. So z is equal to 0 in our case. And now we need to plug in f of z. F of z is sinus z divided by z squared. And then we need to write this expression, z minus 0. Z0 is 0. That's why z minus 0 is just z. Z to the power of which? Z to the power of 1. M is equal to 1. Okay, now this z and this gets cancelled out a little bit. And we have a very familiar expression for you. This is the famous limit, which is equal to 1. So our answer is the following one to this problem. So z is equal to 0, pole of order 1, and the residue of our function in this pole is just equal to 1. That's it. That's it. So out of curiosity, you can use another method to this particular task. Maybe it was much easier to expand this function into Laurent series, of course, no doubt about it. But I just wanted to demonstrate to you how this method works. But you know what? The bad news is that there are some situations which can be approached only by method 3 only. And there's no other way of approaching them. And the good example is our question 2b from our tutorial sheet. So far, we haven't discussed this function at all because it was absolutely unapproachable. Look at this. And moreover, you asked to explore this function not in z is equal to 0, but in z is equal to p. Okay, let's discuss. This is a super difficult function compared to others in this tutorial sheet. Actually, the whole purpose why I decided to record this tutorial part 3 was only because of this example. I was hoping to do without method 3 for you, because the majority of problems they usually apply either method 2 or method 2, but this problem just gave me the idea that you can't do without method 3. This problem can only be solved by this method 3, and even by the method 3 it looks like fancy. You know why it looks fancy? Because we can see that how many singularity points does this function have. Let's start with this singularity points for this function. You need to take denominator and set it equal to 0, and you will end up having to solve this typical trigonometrical equation, and it will give you lots of infinite number of answers. Look at this. All these points are singularity points. Let's write them down. If you take k is equal to 0, you will have 0, pi, minus pi, 2 pi, minus pi, and so on and so on. So this is quite a weird situation because you already been used to the fact that all the given functions have either one or maybe 2 points of singularity. Even if it were three, it wouldn't be a big problem for us. But in this case, they have infinite number of singularities. But luckily, they explicitly tell you they don't bother about other singularity points. Only explore this one. Only explore this one. It's a pity they didn't ask us to explore z is equal to 0, but maybe that's because it's too easy. Okay, let's try and do this. We are armed with our beautiful algorithm, method 3, so maybe we'll manage to do it. So, okay, what is our step? We need to determine the type of singularity. Okay, so it means that we need to calculate the limit of our function in this point. In our case, it will be z tends to pi, unfortunately not 0, of this function z divided by sinus z. Okay, what is our first move when we are faced with the challenge to calculate some limit? We need to just to plug in uh, pi instead of z everywhere and see what happens. So numerator will be pi, denominator will be 0 because sinus pi. And you know what? We are very lucky. This is equal to infinity. This is equal to infinity. So the calculation of the limit looked relatively easy. So our conclusion is immediate. So our z is equal to pi is pole, is pole. But on the other hand, it means that we need to move to step 2. We need to determine the type, not the type, sorry, but order of the pole. But we already have some experience. We need to consider this limit. We need to build this limit. Limit f of z times z minus z0 to the power of m when tends to z0, and it should be equal either to 0 or infinity. So we need to exploit this expression to determine our m. M is an unknown here. Okay, let's build this expression for our concrete situation. So our z0 is equal to pi. That is why we need to consider limit z tends to pi. Here I need to plug in my function z divided by sinus z instead of f of z. And here I need to write z minus pi to the power of m. And now I need to play around with this limit. I need to calculate it, analyze different values of m, and come up with the only one value of m. And I always should bear in mind this limitation. Okay, but how can we approach this limit? You know, if you just plug in pi, it will be pi divided by 0 times 0. 0 divided by 0 is uncertain situation. This is a situation when we are supposed to apply some very well-known trick. And you know what? In our situation, we can do the following. You know, it's always nicer when your variable tends to 0, actually, because when something tends to 0, it's much easier to do our reasoning. That is why let's make substitution. So our z tends to pi, and we are not happy quite it. What if we consider new variable t, which is this guy minus this guy, z minus pi? In this case, your t will be tending to 0, and this is quite a nice news. That's what we are more used to. It's much more convenient. So let's do this substitution. But you know what? So instead of z, I'm going to write some t, but I need to prepare this expression. So z will be equal to t plus pi, and that's exactly what I'm going to substitute instead of z here, here, and here. And t is equal 10 is tending to 0. It's already there. So limit when t tends to 0, instead of z, I promise to substitute t plus pi according to this expression. Here we have sinus of the same guy, t plus pi. And this guy is just t to the power of m. T to the power of m. You know what? Maybe you are not quite convinced with this idea because still this expression looks quite messy. But wait a bit, wait a bit. We are going to simplify it. Look at the nominator, t plus pi, where if you plug in 0 instead of t, 0 plus p will be just p, or not p, but pi. So we can substitute pi here. Now it definitely looks better. What about this sinus t plus pi? You should remember that this expression should be easily simplified, and it is equal to minus sinus t. Sinus t. You should be familiar with these old transformations, these properties from the high school. Okay, and finally t to the power of n. Now it definitely looks better. And moreover, we see this sinus t when t is equal to 0. It immediately brings to mind our favorite beautiful limit. Where is it? Do you remember this famous limit? So we are moving in the direction of this limit, definitely. We need to separate it from everything else. So what can we do actually? You know what? We can actually pull out minus pi from this expression, because the constant coefficient could be pulled out of the limit. Let's do it because it looks much more appealing. So t to the power of m divided by sinus t. Minus p goes ahead all the time. What can we do? We can divide both denominator by t. So t to the power of m divided by t, and sinus t divided by t as well. And that's what we are been craving for. So this is our favorite famous limit, which goes to 0, which tends to, or not to 0, to 1, sorry, to 1. And that is why we can substitute the whole expression by 1. And finally, our limit looks so simple now. Look at this. It's just wonderful. T to the power of m divided by t. And it's pretty obvious. And now remember this limitation. The result shouldn't be equal neither to 0 or to infinity. The only way when it can be done, so when m is equal to 1 again, because t to the power of 1 and t just gets cancelled out, and the result will be 1. A limit of the 1 will be just 1. So minus pi times 1 will be minus pi, not equal to 0 and not equal to infinity. So our conclusion is pretty similar to the conclusion made in some previous examples. The order of the pole is 1 again. So let me write it down. Z is equal to 0. Order of the pole is 1 again. And oh no, it wasn't 0. It was pi. You remember? It was pi. I must have made a mistake. And now we are ready for step 3. Step 3 is about calculation, nothing new. So residue of our function f of z in point pi will be 1 divided by what? M minus 1 factorial. So it will be 1 minus 1 factorial, but it's 0 factorial, which is equal to 1. But somehow I chose to write it this time. So limit when z is equal to z tends to pi, and the order of derivative will be 0. So it means that no derivative at all, but I'm just writing it down. Then we need to write our function f of z, which is z divided by sinus z. And finally, we need to multiply it by z minus pi in order m, which is 1. So that's how it looks like. Okay, so we need to rewrite it in a simplified form because it's super simple actually. So we don't need this d over dz because there's no derivative at all. So limit when z tends to pi of function which looks like z divided by sinus z and times z minus pi. And of course, just like in the previous case, it's much more convenient to make this substitution. So z minus pi gets denoted as t. As a result, t will tend to 0. And instead of z, we need to substitute this expression, t plus pi, just like in the previous case. And I'm going to repeat all these simplifications as well. So instead of z, I'm plugging in t plus pi, sinus t plus pi, and this is just t. Again, just like in previous case, in the previous step even, this guy is equal to pi, this is minus sinus of t, and this is t. I prefer to write it here. And this whole expression will give us 1. This is a famous limit, but upside down. It doesn't matter if it's upside down or just sinus over t, it still gets to 0. So our result is minus pi. So the answer to this problem will be as following. So let's write down the answer to finish with this example. So z0 is equal to pi is pole of order 1, simple pole. And the residue of our function f of z in this point turned out to be minus pi. That's it. So as you can see, the last example was quite a fancy one. And as I said before, I keep repeating it, that the whole purpose of recording this tutorial part 3 was because of this problem, question 1b from tutorial sheet. Hopefully, maybe you will not come across this problem in your exam, but who knows? That is why I decided just to give you the whole picture, which turned out to be quite time consuming, of course. So, and the most important thing to make conclusions, to make proper conclusion of all these three parts, because as you realize, we sort of got stuck at this the first two questions of tutorial 12. It's already recording number 3, and we still haven't moved any further. But that's how big this topic is. So the questions 1 and question 2 from tutorial 12, they are all devoted to the same topic. Find the point of singularity for given function, and I'm trying to improve my camera, and calculate the residue in this singularity point. So what is the best course of action for you? What is the review of all these three methods? So let's write it now. How to approach the task of determining, sorry for my, the type of singularity, and calculating, and also calculating residue of the function in this singularity point. What is the best approach? So when the first consideration should be start with Laurent expansion. This is the best one. Start with considering Laurent's expansion. Laurent's expansion. Because this is the best. Why is it best? Because if you manage to expand your function to Laurent series, you don't need to bother about this formula for calculating residues. You are killing two birds with one stone, quite literally. You immediately see the type of your singularity, and you immediately see the residue, because the residue, remember, this is this coefficient. So that should be your first thought. If you find however, if you find your function a little bit difficult to bother with expansion, or maybe absolutely impossible, then consider method 2. Consider method 2. Method 2. Method 2 consists of, you need to determine if your function has this special structure or not. So if you observe that your function has this special structure, and of course with the requirement number 2, which is about nominator not being equal to 0 at the point of z0, then you are lucky again. You're lucky once again. So it's because this, even though this method is suitable only for poles, but as I said before, poles are quite popular in the problems for students. So maybe you will be lucky. And as for formula for calculate residue, I don't think it's it's so terribly difficult, more difficult than Laurent's expansion. And only if both these methods don't work for you, you should consider method 3. Consider method 3. Method 3 only like as a last resort, at the last resort, because as you can see, it's quite a fancy method. It does require it does involve a lot of calculation. That is why it doesn't look so appealing as the first ones. But who knows? Who knows? You should be aware of this method, and you should bear it in mind. Okay, so this is the end of tutorial 12 part 3. Finally, eventually, we finished with this huge topic. And the next tutorial will be devoted to, next recording will be devoted to calculation of contra integrals using this tool.